Welcome to STAT200. This lesson is about measures of dispersion or width of a data set. Last week we considered measures of centrality. Let's review that briefly. We learned how to compute the mean, which is just the average of the data set. It's the total of the values divided by the count. When we're referring to the sample mean, that's a sample statistic, we use the symbol X bar. And when we're referring to the population mean, a parameter for the population, we use the symbol mu, the Greek letter mu. The second measure of centrality we considered was the median. It's the middle value, or more precisely, it's the middle value if n is odd. But if n is even, it's actually the average of the two middle values, the values adjacent to the line that splits the data set in half. The mode is the most commonly occurring value. So by way of review, let's look at this little data set with elements 5, 11, 14, 15, 16, 16. If I add these values up, I get 77. I divide by 6 because there's 6 values, and that gives me the value 12.8333 approximately. The median, this data set has an even number of values, so I split the data set in half here and average the two middle values, 14 and 15. So I get 14 plus 15 over 2, that's 14.5. So 14.5 lies exactly halfway between 14 and 15 and splits the data in half. 3 values smaller, 3 values larger. The mode is 16 because there's only one value that's repeated. There's 2 copies of 16 in the data set, and all the other values only occur once. Okay, but let's move on to our measures of dispersion or width of a data set. The simplest measure of dispersion is called the range. It's simply the distance between the minimum value and the maximum value. That is, I take the maximum and subtract the minimum. Gives me the range of the data. Here's an example with the same data set. It's clear that the minimum value is 5. The maximum value is 16. Note that minimum and maximum are also statistics when I can determine them from a data set. So the difference between them, 16 minus 5 is 11. So 11 is the range of this data set. This may seem like a very simple statistic, but it turns out that for very small data sets with only 3, 4, or 5 elements, the range is actually the most reliable, most useful measure of width or dispersion. But the focus of today's lesson is on the standard deviation. We saw last week when we computed the sample mean that the deviations from the mean always add up to 0. So we can't use the average distance from the mean simply by averaging the deviations, because we'll always get 0 for an answer. And the reason for that is the mean is always larger than some of the values and smaller than other values, so I get a collection of positive deviations and negative deviations. And by the way the mean is defined, these deviations always add up to 0, making the mean the balance point for the data. Well, one way to fix the problem is to simply use the absolute value of the deviations. That is, just make them all positive. That's possible, but it turns out it has some problems mathematically. A smoother way to make all the deviations positive that doesn't give us mathematical problems is to square the values. So consider the table below. We have 6 values numbered 1 through 6. The values are 34, 16, 30, 29, 36, and 17. First thing I want to do is compute. To get the distance from the mean, I compute the mean. I add these values up. I get 162. I divide by 6 because there's 6 values. 162 divided by 6 is 27. So 27 is the sample mean. I copy that into this column for reference, because now what I want to do is compute the distance of each value from the mean, the deviations. So 34 minus 27 is 7. 16 minus 27 is negative 11. Notice I keep the sign, I subtract. 30 minus 27 is 3. 29 minus 27 is 2. 36 minus 27 is 9. And 17 minus 27 is negative 10. And if I add up these deviations, and you should do that, you'll see that you get exactly 0, as you always do when you can add up the deviations from the sample mean. But now to make them all positive numbers, I square them all. This is a nice smooth mathematical operation. 7 squared is 49. Negative 11 squared is positive 121 because negative 11 times negative 11 is positive 121. 3 squared is 9. 2 squared is 4. 9 squared is 81. And negative 10 squared is positive 100. So these are my squares of my deviations from the mean. If I add these up, I get 364. So now I can compute the average of the squares of the deviations by dividing by 6, dividing by how many there are. And I get the answer as 60.6667, or 60 2/3. Well, if you look at the deviations, they range from negative 11 to positive 9, so this certainly doesn't look like a deviation that represents this set. The reason is that we squared all the numbers. So to, in effect, undo the squaring, I can take the square root of this final answer, the square root of 364 over 6, to undo the squaring, and I get that the standard deviation is the square root of this answer, about 7.8889, and that does look like a reasonable measure of the average distance from the mean. So in general, how do we compute the standard deviation? Well, we follow the process that we just outlined. We compute the mean of the values. We compute the deviations from the mean by subtracting x bar from each of the values. So I get a list of deviations, one for each value. I square all those deviations to get the squares of the deviations. I compute the total of the squares of the deviations by adding up everything I got from step 3. Then I compute the average of the squares of the deviations by dividing by the count, n. And then finally I take the square root of that result from 5. So this is the formula for the standard deviation. Technically, the formula for the population standard deviation. Notice I use the Greek letter sigma here. That's a lowercase s, Greek symbol, sigma. So how do I compute the standard deviation? I take the square of the sum of the deviations from the mean squared, all divided by n. But it turns out this doesn't work exactly right when I compute the sample standard deviation. I need to make a small adjustment. So when we compute the standard deviation of the sample, it tends to underestimate the true population standard deviation. Remember when we computed the sample mean x bar, we said that it was a really good guess, a really good estimate of the population mean, especially if the sample is unbiased, a good representative sample. Well, using this same formula, the standard formula for the standard deviation, it turns out that doesn't work well for the sample standard deviation. It tends to underestimate the true population standard deviation. So to boost the standard deviation, to make it a better estimate of the population standard deviation, we divide not by n, but by a slightly smaller number. When we divide by a smaller number, we get a bigger answer. So for example, if the sample size is 25, instead of dividing the total of the squares of the deviations by 25, we divide by 24, making the answer slightly bigger. If the number of values is 9, then instead of dividing by 9 in the calculation, I divide by 8, getting a bigger answer. So this is the formula for the sample standard deviation. This is the one we'll use. The population standard deviation, the population parameter, is called sigma, and it's the population standard deviation. The sample standard deviation uses the symbol s, and it's a sample statistic. So in this class, we'll almost always work with sample data. So we'll almost always work with this formula, the one with the slight reduction in what we divide by. In a very rare case, where we're given the entire population data and told we have the population data, then we would use the first formula. But almost always, if not always in the class, we'll use the adjusted formula for the sample standard deviation. Let's work through an example of computing the sample standard deviation. So given the data set 26, 22, 9, 12, 16, I add these values up and divide by 5 because there's 5 of them. Notice when I compute x bar, I always divide by the full count. I never make an adjustment for the sample mean. When I do that, I get 17 as the result. Okay, the magic of video editing, yes. So it's x bar is the total, 85 divided by 5 is 17. So now to get the deviations, we subtract 17 from each of the values. 26 minus 17 is 9. 22 minus 17 is 5. 9 minus 17 is minus 8, etc. So these values represent the deviations from the mean. And again, if you add them up, you'll get 0. So now I square each of the deviations. So 9 squared is 81, 5 squared is 25, negative 8 times negative 8. Negative 8 squared is positive 64, negative 5 squared is 25, and negative 1 squared is 1. So now that I have the squares of the deviations from the mean, I add them up. I get 196. And now I divide by not n, but n minus 1. In this case, n is 5. There's 5 elements in my data set, so I divide by 1 less. I divide by 4. The result of that calculation, before I take the square root, actually has a name. It's called the variance of the data set. We'll focus on using the variance much later in the course. But the variance is simply the square of the standard deviation, so its symbol is actually s squared, reminding us that if I want the sample standard deviation itself, I take the sum of the squares of the deviations, divide by n minus 1, and then take the square root. So the square root of the variance, the square root of the sum of the squares of the deviations divided by 1 less than the count, gives me the sample standard deviation. So in this case, my S, my sample standard deviation, is 7, indicating that 7 is, in some sense at least, a measure of the average distance of the values from the mean. Okay, so now it's your turn to practice this. Given the data set with values 47, 88, 56, 75, 55, 43, and 77, first compute the sample mean in the usual way, add them up and divide by the count. Compute the sample variance by computing the deviations, squaring them, and dividing by 1 less than the count of the number of elements in the data set. And then finally the sample standard deviation by taking the square root of the variance. So please pause the video, take out a piece of paper, do this work, maybe make your own table to help with the work to show all the steps. And then after you've completed your calculations of the mean, the variance, and the standard deviation, you can continue the video and I will reveal the solutions. Okay, so hopefully you've done that work. You've computed all the statistics, the mean, variance, and standard deviation for this data set. Let's compare answers. So I used a table for the work. I listed the values 47, 88, 56, 75, 55, 43, and 77 in the column here, numbered the values, x1, x2, x3, x4, etc. So first thing we do is we add up the values. I get 441 as the total. There's 7 values, so to compute the sample mean x bar, I take the total of the values, 441, divided by 7. That gives me a sample mean of exactly 63. I record the 63s in the next column just as a reminder for doing the subtraction. And then in the fourth column here, I compute the deviations from the mean. 47 minus 63 is negative 16. 88 minus 63 is 25. 56 minus 63 is negative 7. 75 minus 63 is 12. 55 minus 63 is negative 8. 43 minus 63 is negative 20. Notice I always subtract the mean from each value. That's why sometimes I get a negative answer. Finally, the last one is 77 minus 63 is 14. So these are the deviations from the mean, and if you add them up, and you should to check, the total of all the deviations is 0. There's just as much negative deviation as there is positive deviation. So now to work toward computing the standard deviation, I take each of the deviations and square them. So the square of negative 16 is positive 256. The square of 25 is 625. Negative 7 times negative 7 is 49. 12 times 12 is 144. Negative 8 times negative 8, or negative 8 squared, is 64. Negative 20 squared is positive 400, and 14 squared is 196. So when I add all these squared deviations up, my total of the squared deviations comes to 1,734. So to compute the variance, I simply take the total of the squares of the deviations and divide by 1 less than the count. Divide by n minus 1. 1734 divided by 6 is 289. So 289 is the variance of this data set. And then finally I get the square root by taking the standard deviation, by taking the square root of the standard of the variance. So s is the square root of 289, which is 17. So 17 is the standard deviation, the sample standard deviation for this data set. Okay, so that's how we do it. One more important idea, now that we know how to compute the sample mean, a measure of centrality, and the sample standard deviation, a measure of width, we can use these to tell us where most of the values lie, not only in the sample, but also in the population, if I have a good unbiased sample. So we're going to describe now this empirical rule that lets us use the sample mean and standard deviation to figure out where most of the values are located. Again, it works for the sample values, but most importantly, this gives us an estimate of where most of the population values fall. Here's the rule. 68% of the values fall between the mean minus 1 standard deviation to the mean plus 1 standard deviation, within that range. 95% of the values fall between the mean minus 2 standard deviations to the mean plus 2 standard deviations. And 99.7, almost all of the values, fall within 3 standard deviations of the mean. That is x bar minus 3 times s up to x bar plus 3 times s. So by way of example, we can consider a data set where the sample mean was 208 and the sample standard deviation was 32. So 68% of the values, the central 68% of the values, will be found between 208 minus 32, that's x bar minus s, up to 208 plus 32, x bar plus s. Well, 208 minus 32 is 176, and 208 plus 32 is 240. So this range, 176 up to 240, will hold the central 68% of the values. Almost 70% of the values will fall in that range. 95% of the values will fall between the mean minus 2 standard deviations to the mean plus 2 standard deviations. That's 208 minus 2 times 32 up to 208 plus 2 times 32. Well, 208 minus 64 is 144. 208 plus 64 is 272. So this interval from 144 to 172 will hold 95%, the central 95% of the values will fall in that range. Only 5% of all the population values we would expect to fall outside this range. Finally, almost all of the values, 99.7%, will fall between 208 minus 3 standard deviations up to 208 plus 3 standard deviations. Well, 208 minus, that would be 96, is 112. up to the mean plus 3 standard deviations. That's 304. So almost all of the population values will fall between 112 and 304. Again, if I've got a good, fair, unbiased sample that's well representative of the population. But this is really amazing, actually. Only two numbers, the sample mean and sample standard deviation, give me a real picture of where most of my population values lie. This is a very useful rule, and we'll make heavy use of it as we move forward in the course. Why does this work? Well, this empirical rule actually comes from the normal distribution, which will be a big subject of study later in the course. If our distribution of our data looks sort of like a bell, the so-called bell curve, where the mode and the median and the mean are all the same place and the distribution falls off smoothly on both sides, then about 68% of the values fall within plus or minus 1 standard deviation, from the mean minus 1 standard deviation to the mean plus 1 standard deviation. 95% of the values fall within 2 standard deviations, technically within the mean minus 2 standard deviations as my lower limit up to the mean plus 2 standard deviations as my upper limit. And 99.7% of the values fall within 3 standard deviations. These numbers become precise when our population actually has a normal distribution, but they're a good estimate for many, many population samples we get from populations. Notice that only a tiny fraction of the values, 0.3%, that's 0.15% above and 0.15% below, fall outside of this 3 standard deviation interval. Okay, so for homework, study this video before class on Tuesday, very important. On Tuesday, you'll get practice computing the standard deviation. You'll learn how to check your work using the TI-84 calculator. You'll get practice using the empirical rule, what I like to call the 68, 95, 99, 7 rule. You'll have a quiz on last week's material on measures of centrality, and your graded quizzes from last week will be returned. Those grades you'll also find on D2L before the end of today. Okay, well that ends this lesson. Please make sure you prepare well for class and make sure you go to class on Tuesday.